The oil plate.
Good. So on Monday we discussed about this torque to speed characteristic. So as I mentioned, that's a really important characteristic. You all need to fully understand what it is. So you just repeat again, make sure you do understand that. So the horizontal x-axis is the speed here. So you can see that when the motor starting, we have starting here, right at that point. So the speed will be equal to 0 here. And then the speed will increase, and then can also see the top profile increase in such a way. And at a certain point, we call this called the breakdown. So the name, we call it the breakdown sleep. We also call the breakdown speed, and also breakdown torque. They're all everything called breakdown. I think that probably the name will come from, there's a maximum capability for the motor. Whenever beyond this one, then the motor could break down. So you just give a name called the breakdown. And the normal operation will be mainly in this region, because you can see that naturally the torque and speed are more realistic for natural phenomenon. For instance, when we increase the torque, the speed will decrease. So that means if we increase the torque in this way, then we can see that the speed will decrease and vice versa. That will be a more natural way we can able to understand how the loading effect of a motor. That loading effect appear for all the system, like electrical system or battery system. We also have such loading effect anyway. And then right at that point, this point is where the frequency of rotation and the input synchronous frequency were the same. So in this case, because they're the same, the motor is not having any induction. So that means induced EMF or induced power in the motor becomes 0. We have no power at all. So that's why I can see at that point, the torque will therefore equal to 0, have nothing coming out. And then if the speed go further in here, then we call it the power regeneration. The power regeneration means the power will be reversed from the rotor back to the stator. Anybody can tell me why this region will become power regeneration? Of course, from the label here, we have the motoring region. So this region will be motoring. When we move on to this region, we call it power regeneration, generating. That means if a motor is generator, it operates on this region. If a motor is a motor or vehicle going down the hill, then we call the power regeneration this region. So
Is it because the torque is negative? That it's okay.
Yes, one thing you can see the torque is negative. But of course, any other phenomena you can observe from here besides torque negative, we know that will be more in the constant operation. The power regeneration will be in constant 2. In constant 2, then of course the torque will be negative because we're reversing the torque. Yeah. Instead, the motor giving the torque to load, and then but now the load of the rotor, we're giving back the torque back to the system. But another thing we observe that will be the frequency. One thing I like to see that if you're now looking on a power source or maybe an inverter to drive the motor, how you can force the motor to operate in the motoring and also in power regeneration. You see, when you say torque, then it's quite difficult to control the torque, right? The torque usually the motor will generate certain amount of torque in here, so you can tell the motor at certain operation of the sleep, then you can have certain torque. So this torque should equal to the load torque. That would be the one you drive the electric vehicle, the friction all add together become your torque requirement. That's how the motor generates torque. And then somehow, when you further increase the speed, then you go to power regeneration. How we can make the motor regenerate the power from the motor back? Because you say, oh, negative torque, yes. Under power regeneration, we have negative torque. But how do we control inverter? how do we control the power source to make it become power generation? So that highly relate to how we control the motor. So later on, next chapter, we're going to look into the motor control, how to control the motor. Yeah, then that's more interesting. That's all basic equation you feel really confusing, but how to control motor will be more interesting. Anyway, so what is that? How do you think? How are we going to control them to make it become power generation? We can transit from motoring to power generation, quadrant 1 to quadrant 2. You see in the midterm or in the homework, I asked you for the DC motor, when we change from quadrant 1 to quadrant 2, what we did is to reverse the polarity, yeah? The input, then you can reverse the motor. However, if we want to go to power generation, we can reduce the voltage for the input, make the back EMF higher voltage than the input, then become power generation. So in this case, how are we going to do that? Any recommendation? What do you think? And can you observe this curve? What can you see? What can you do to make it happen?
Our synchronous speed would be lower than our rotor speed.
Excellent. Yeah.
Okay.
All the operation, we are using single frequency of input from the stator. That's the synchronous speed, right? And then the rotor speed will be provided by this curve. So for either at that point, there's a certain speed of the rotor will give us the maximum possible amount of torque. But during that time, the input frequency from the rotor, from the stator unchanged, still say 60 Hz. And then we continue to increase it, the rotor speed until this point, then the rotor frequency will equal 60 Hz, equal to synchronous. Then there's a no induction. And then you can see that when we further increase the motor speed, the motor speed or the rotor speed will be higher than the synchronous frequency, higher than 60. Then in this case, we can power generation. That is what you can observe here will be, if you want to go for power generation, the rotor is a higher frequency than the stator. Then the stator input, or put it another way, if you want to change into power generation, you just decrease the frequency of input slightly, just less than the rotor rotation. Then you can power generation. That's a really long goal. Our power source has to control the rotor to rotate at certain speed. That speed usually will be close to 60 Hz or slightly less than 60 Hz. Yeah. And then when the motor rotates too fast, like you're going down the hill, then you originally control at 59 Hz. But now going down the hill, the gravity will cause the rotor or the motor vehicle to more than 60 Hz. Even high frequency, then your supply inverter or source, then the power will therefore regen. So that's the concept, how we can transit from motoring to power generation. So that is, in the future, when you control electric vehicle or wheelchair or motor, that's how we control it to make it power generation, how we change it from quadrant 1 to quadrant 2. All right? So that's quite interesting here. So last week, Monday, we also discussed why this become unstable, because that is not logical for our power operation, because there won't be any loading effect. So that's how we can review from here. So that means we discussed about the unstable region, that is the loading effect we try to avoid. We also call it the low point of return, because if we try to decrease the load torque, the motor speed also decrease. Somehow the motor will go to store in here, become zero speed. So this region is not the normal operation of the loading effect. So then could happen when we spend too much time when we have the motor to start, too low voltage or not sufficient flux to motor start, or the load will be too much load, too heavy load, and then there will be voltage dip. The voltage become lower than we expected. For instance, we are driving motor at 120 volt AC, but that's a normal voltage, but now you're driving low voltage, or suddenly the input source has some voltage unstable, voltage dip. So voltage dip will be something like that, hit a sideways, and suddenly this become voltage dip, or sometimes the whole voltage have a voltage dip here. That also happens. Why it happen voltage dip? Because, for instance, we are using 120 volt here, but if some large power source nearby or large load nearby turn on, you draw too much current, then because loading effect, the voltage here will be lower than expected. Then we call it loading. That's called the voltage dip. So voltage dip is quite usually happen when we have some heavy load nearby. Then in this case, we'll have some stalling condition to happen. Then, of course, once it happens, what we can only do is just restart the motor. That's all. And the stable region is the region we try to operate. So that means for the stable region, that is our stable region. Even though for power regeneration, right, this is also our stable region too. So these two regions, because when a vehicle changing from quadrant 1 to quadrant 2, then these two regions can be always interchange operating. For instance, a vehicle, when you're motoring in quadrant 1, when you see a traffic light stop, then the energy will be turned to the battery. So that will be, they will change between these two, right? Once the traffic light turn to green, you go again. So that's how it happen. So the low region here, you can see that without too much load, then the slip will usually really much close to here. Then the slip will be quite really small. You see the cross section here, the S equal to 0. So without any load, then usually happen in really small slip, and heavy load will go to this region too. So that means this is the normal operation region. So all these things we have already discussed on Monday, how the characteristic of the load look like. When we increase the speed, the torque will drop and so on. So the maximum possible or the breakdown torque will be here, but the rated torque, the normal operation of the torque, we usually do not choose the possible maximum torque. And you usually choose about half of them. But of course, that is not a rule of thumb. For some operation nowadays, they try to move the rated torque to more close to the breakdown torque. Why is that? Of course, the principal operation will be quite straightforward. Maximize the performance, reduce the cost, right? Before we cannot do that because the cooling or the design of the motor may not be too good. Once you try to always operate at the breakdown torque this region, the motor get really hot. So in this case, may not be too good for the motor too. However, today we mainly try to use very nice cooling method. For instance, we have forced liquid cooling. So even though we operate at high power, we're able to remove its losses quite rapidly. So in this case, sometimes we're able to more approach to this breakdown torque value. May not be equal to all the time, maybe 80%, 90% also possible if we tend to use the forced cooling on the motor. So next, we try to move on to more practical motor design. But for motor design, at the moment, we always talk about motor, we try to confine to the motor characteristic, but more toward the single-phase operation. But of course, the motor, we do a three-phase and single-phase operation. But here, before we go for the three-phase operation, we try to show you what three-phase is. Maybe some of you have learned the three-phase, but just ask some of your friend and my colleague, you still haven't learned the three-phase system yet. Even though for the EE65 or Engineering 65, you only stick to single phase, right? So have you done any three phase yet? No? In here, I just give you a really brief understanding for three phase system. And I'm not quite sure Engineering 65 will teach you the three phase, but we'll try to ask them to teach you the three phase property. But in here, I just show you some basic principle for three phase so that you do have some idea what they are. For electrical engineer, everybody must learn three phase because the basic requirement. You have to learn that. Because here will be single phase, but out there, everything will be three phase. You can see all the power line, the power distribution, power transmission. You always can see three very long cables, right? They're not two, they are three because they're three-phase system. For power transmission, power distribution, we always using three-phase system. So like in here, your typical three-phase system, because they phase A, B, and C, sometimes we can use L1, L2, L3. So there's a different terminology. So depending on which one notation you use. So anyone that can be done. But 20 years ago, people tend to use another terminology. They call it red, yellow, and blue, but we're not using it anymore. So they use these three colors to identify different phases. And then, but however, that have been used for more than 100 years. But since 20 years ago, we try to abolish this method because of the many engineers, they are colorblind, they're not good in distinguish three phase. They get big problem. So now that they got the new color code for here, that color code means about gray, blue, they're not that be an issue for colorblind and engineer. Before for an engineer, we have more male than female. So it happened to be like that. So we gradually move on. So we are now not using this anymore. We just call it L1, L2, L3 for phase A, B, C, that's all. But anyway, so you all know the three-phase system must be 120 degrees between them. So in this case, you can see that we got each of phase, they different by 120 degrees. So of course, this equivalent to 120. So that's, and then we have the phase voltage and line voltage here. So for instance, that is so-called Y or star connection. So sometimes we call it Y, but sometimes we call it star connection. Of course, we do have something called a delta connection. So they're quite similar, just how we connect the three winding together, like the three-phase transformer. We can connect them in three-phase in star or delta. So you can see that each of the phase voltage, for instance, from any one of the line to the neutral is the common point for all the three-phase systems. So that means for the power point we measure in here, that is the phase voltage because they only give you these two lines. But although this room is any one of the phase, but another room, another building, there could be another phase. So that to say, if you want to enlarge the power, don't just parallel this to the other socket there. That can be very dangerous because these two can be different phases. Different phase, that means the voltage will be given by this formulation. They are different by 120 degrees. The instantaneous voltage are not equal. So if we put them together in parallel, that will be look like short circuit. So don't do that. So because you never know which phase are using in which socket. Of course, for your own house, probably you only have single phase at your own house. But sometimes for some house, they are supplied three phase, and each of the socket in each room could be different phases. So you also need to be careful. And then the other phase operation will be you call the split phase. So split phase, that means you have 120 volt, but some houses, they have use high power, like washing machine, maybe charging system, your cooker charger, they need to use split phase. Split phase, that means, anybody can tell me what is split phase? I think your house, you have that, right? Everybody, have you ever spent some time on your house to see how the socket look like? What voltage are they? You try to measure the voltage, you see the label, what voltage they are. you're now electrical engineer or engineer. You need to tell your parents, say, oh, I know all this. What is the voltage like? What kind of the phase voltage, line voltage, split voltage? Three phase, you need to know this, right? Yes?
Yeah.
What's split phase?
Split phase would. Assuming it's essentially just, instead of it being 3 phases, 2 phases. Connected to neutral, the difference of 180 degrees.
More than that, yeah, something like that. You see, in here, each of phase will be have 120. So when these two of the phase from here, you measure them, for instance, A and B are different by 120. And then, so this 120 refer to neutral, this 120 refer to neutral. But when you measure these two voltage, they're not 240 because they have phase angle, they're better. The phase angle 120. You need to use better sum. But however, for some houses, they use split phase, so they're two phase 180 degree to each other. So what you say is right. So if they're 180 volt, so the difference between two phase becomes just 240. So some of the house they use split phase. So that means they, for instance, they have L1 here, and then they got L2, and they got a neutral in here. Then this is 120, this is 120, but L1 equal to some voltage, say A voltage sine omega t, and this voltage will be equal to A sine omega t, and then minus 180 t. So, and then the voltage one is like that, the other one will be like that. So when we get the difference between them, it's just summation of two voltage. If there's split phase, then we have 180 degrees each. So that's one of the examples. So take your house with a normal household, usually we have single phase or split phase. Split phase, you go to your cooker and your washing machine, or maybe charging system. But if you are even high power, then your house will supply by three phase, like this, and the voltage between them will be given by this formulation. Then you can see that the voltage between them will between any one of the phase. So now this is 120, 120, but the difference between them is not 120. They got phase angle. After some trigonometric function, you end up with a √3 in here. And then the phase angle become, as compared to original one, also have a phase angle between them. So that means now then the voltage will become a √3 relationship, right? So that means when you calculate the single phase voltage to the line voltage, there will be √3 relationship. Yes.
Just because, like, I don't know, like, what 3-phase assembly, why would you need a 3-phase instead of like a 1-phase? Like, what's the difference between using a 1-phase and using a 3-phase? Is it just so you can have more voltage spread out?
You see all the high power system, all the power generator in any power plant, they used to come up with the 3-phase. Because when you have high power transmission or long distance transmission, you used to come with the 3-phase system. And then when 3-phase, why we doing that? Because for instance, for 3-phase transformer, then the power will be more balanced. When you rectify the 3-phase into DC, the DC has less ripple. Somehow we need to convert the 3-phase into DC or DC into AC to have the voltage conversion. And also for the 3-phase transformer is more balanced, then the transformer can utilize much better. The transformer becomes smaller. So for power distribution, power transmission, we tend to use 3-phase, everything becomes smaller size. You see when you transmit the power using single phase. So that means your 2 wire are going this way. So at least use 2 wire, but you can only transmit 1/3 of power compared to 3-phase. But for 3-phase, you only need 3 wire, and they can transmit 3 times of this power, but we're only using 3 wire. So they save a lot of transmission costs. So that's why for high power or long distance, we have to use 3-phase. And then you also see one of the homework we are using, the transformer, right? 3-phase transformer, something like that, right? This transformer, I asked you about the middle here. What is the size for the centrally here. Is it 3 times of this one? No, it's the summation of first here is less than or equal to 0. So mid slim here can be really, really small because of low magnetized. So that can also reduce the size of transformer. You can see that if you use 3 separate transformers, you can also change the voltage for 3-phase, but the transformer will be much bigger than that one. You look at a 3-phase transformer, you can reduce the central limit. Anything you can cancel out. So like in here, the 3-phase, why we don't need a return path? We can have a return path in here because the 3-phase, they all differ by 0, 120, 240 degrees. The summation equals 0. So the return path of the current will equal to 0 current. And so we don't need that at all. So that's why for high power transmission, 3 wire will be sufficient. So that's safe, energy saving, material saving. So this kind of trigonometric function, I don't need to go through them, very straightforward. You just some formulation, you can work out. Here you can see that the voltage between the line and phase voltage P for phase voltage, you amplify them by 1.71 something with 3. So that's to say, when you see the 3-phase voltage, the voltage is not double. It's only 1.71 times with 3. So that's slightly different from the split phase. And the phase angle between them also a phase angle. You can check about the phase angle for single phase and 3-phase there with phase angle relationship. Anyway, so that's to say now then, if we draw the diagram for 3-phase, so we got 120. So this relationship for line voltage have a root-3 relationship. And then after we did that, then we can see that for line voltage here, that's the line voltage. And then we can have phase voltage amplitude. Of course, we have 3-phase, root-3 in here, that's important. And then you can, so this combined together, we call that the amplitude of the line voltage. And then you can see that the original is only sine omega t, but now we got the pi over 6. So the phase angle between the phase voltage and line voltage have a pi over 6 relationship. So that's to say, when you have a sine wave, you have a phase voltage, sine wave, and the line voltage will be higher amplitude, and then they also have phase angle between them. So I did some simulation testing, like in here. So here we got the 3-phase voltage in here. So the 3-phase voltage, we use different color for 3-phase voltage. And then if we go for the line voltage, then you can see that there's a phase angle between them. So that would be 30 degrees. So line voltage is 30 degrees ahead of the phase voltage, which really simple, straightforward. You can use the trigonometric function. You can calculate it. I think you all can do that. That's a very standard. All the websites have shown you how to do that. So similarly, when you have phase A like that, and phase B and C will also similar, but using another 120 degree angle, also have a phase angle of 30 degrees between them. So that's a directly we can use a trigonometric function identity to prove that. So the key thing we observe in here will be root-3 relationship between phase and line voltage, and also we have 30 degrees between them. So that's to say, you got 120 volt in here, but if your house supplied by 3-phase, that would be 208 volt, roughly about that. Any question? Yeah.
This might be a bad question, but why did we stop at 3-phase? Is 4-phase possible or 5-phase, or is that?
No, that's an excellent question. So, 4-phase doesn't make any sense. In 4-phase, they all 90 degrees to each other, doesn't give you any sensible choice. Their system for 5-phase, something even number of phase will be also possible. But we found that for the high power transmission, using 5 wire is quite inconvenient. So 3 wire will be good one. And then you see that when we have 3-phase rectifier, then the ripple, you can have 3-phase system here, right? 3-phase system, 3-phase system. And then when you rectify them, then you will have then you end up all the ripple adding together. We usually rectify the AC into DC anyway. So the ripple here will be quite small already. We don't need 5-phase to make the ripple voltage to be so small. So we found that 3-phase will be sufficient. It's a balance between the material we use and also the quality we want. High number of phases just make the ripple become small or more balancing, but that doesn't give us a good credit when we compare the material use. So here is trying to illustrate what we're doing. We got phase A, B, and C, yeah. And then we do have neutral. Neutral we usually don't need to present that. So you can see that phase voltage and each of the line refer to phase, we call the phase voltage. Between the two phases, we call it the line voltage. That's all. Yeah. And then the voltage between them will be √3, and the angle between them will be 30 degrees. So that's the key thing you do. Remember, if you like, you can define the formula using the triple function. You can always define it quite easily. So that's it, the key point what I need to tell you about the three-phase system. So the three-phase can be quite complicated, can be quite simple. I just show you the result and then that's all, right? Any question up to here? Why we need to teach you three-phase? Because all the motor, all the machine, wherever is high, more than 3 kilowatt, we tend to use the three-phase. Anything less than 3 kilowatt, because we don't care too much about ripple and power factor, then in this case, the single phase will be more dominant. Yes.
So how would we wire this up to our induction motor? Would there be more terminals or would it be?
That's also a really good point. You see, when we operate on three-phase, induction motor need to have the neutral. So all the motor, actually, we only put 3 wires to the induction motor. The induction motor have a 3 terminal, which only our three-phase A, B, and C. Many of motor may not have the neutral connection, but of course some do have. And then when you see an induction motor, many induction motor, when you come to your factory, they will have 3 separate windings to you. So we have 1 winding here, 1 winding here, 1 winding here, like that. So you got A, B, and C. Probably we call A dash, B dash, and C dash. So you see the winding voltage will be fixed. For instance, the maximum voltage will be 120 for each of the winding. You can connect them in delta or star by you. You can, for instance, if you want to connect in the star, you just connect these 3 together. This will become a neutral. So you just putting 3 phase into here. Or you can put them into delta. Connect your delta. So A dash, A dash, A, and then you have B and then B dash, something like that, and then you have C and C dash. You connect them up. So the way we connect them into delta star, mainly about operation. Because you can see that our 3 phase will connect to this point, and this point. Your 3 phase voltage usually provided by the power company or by a building. So that will be, say, 208 volt. So to 208 volt, you can either connect to the whole winding here, you got more voltage to each winding. But if you connect to here, then you have 208 volt connect to 2 winding. So you got less voltage for each winding. So that depends on your motor rating, voltage rating, or depend on how much voltage you want to connect to your motor. For instance, some motor, when you start the motor, you don't want too much current on the motor. You may go high current and damage the power system. Then when you start it, you first using the star connection like this, you have less voltage to each of the winding. So the starting current can be lower. So once the motor can pick up the speed, then you can reconnect them into the delta using some configuration, maybe some breaker or something. Then you have full voltage to the motor. So this method is very popular. We call it the star to delta starter. So that's also one of the way we try to control or start the motor. Those are not technique when we do. And then you can see that some three-phase system, sometimes they connect the motor already for you. So that means when the motor come into here, you have a motor here, you got 3 wire, say A, B, and C. They do have a neutral here for you because if they are star connection, they do have a neutral. So you can also connect the neutral. And then some motor, if they provide to you already in delta, there won't be any neutral. So that means for three-phase system, you can see that some three-phase system, they call it 4 wire. So 3 phase, but we call 4 wire. That means they have the neutral. But if a 3-phase system, if 3 wire, that means we have no neutral, no N winding. So that means that will be A, B, C as the N neutral. So that means three-phase, we do have many different kind of the configuration or the driving. So you can go back home, you can see for all your equipment, sometimes the three-phase system, they have 4 wire and 3 wire, depend on it's a star or delta connection. Or some of them can be flexible, you connect yourself because they give you 6 connections, you can do your own connection. Yeah, so I love the flexibility, three-phase. And then one question will be when you see the power distribution, we always have 3 lines, that will be 100% sufficient. But occasionally you can see the neutral. Yeah, but sometimes you may think about how do we, if I want a neutral, what we can do. For instance, here we have 208 volt per line voltage distributed to your house. And then your house, you need to convert into this socket. This socket only base voltage, never can be line voltage. How do they do that? How do they give you back your neutral? They will not prepare neutral in the power distribution, in the power transmission. It's raising their thing, or raising their copper. So only go to your house, they will create a neutral for your house, right? So that's another thing. Of course, my lecture here is electrical machine, not power system. If you want to learn more about this, go to the next lecture, power system. That will be really important. Then you know how is that power distribution, how transmission look like, how the compensation, how is the power player look like, how to connect to the power line. There's many things there, like the voltage speed and voltage regulation, how to use capacitor, inductor to compensate under fault condition. Fault condition means in case one of the lines suddenly have short circuit or a fault to the ground, then the power will be disrupted. Then how the power company try to resolve the problem. So occasionally you can see that in the theory day or some heavy duty day, then some from the phase being broken, then the power will be shut down. Then how the power company can resolve that problem. And what's the technique they tend to use? There's so many things there. So I think you all need to learn that. Today, our power distribution or power transmission in the whole country have been used for 200 years. So they are really vulnerable, very weak. We call them weak grid. So they are. So they need to be remembered. Nothing has been changed for the last 50 years. Even though we may have a new technology in power electronics, they didn't change anything. So I think for the next 10, 20 years, there's many new systems being added to our power system. So there's unlocked the job opportunity. So if you go for the power electronic power system, electric vehicle, then unlock the job. Anyway, what I'm trying to say will be because AI will be also wonderful, but however, you never know AI what will happen. AI will be trying to replacing some of computer science people. So many of the jobs in the last couple of years, we got less job opportunity for computer science. But however, for power, we see a good future. Like, because I'm sure that today we got 8% of electric vehicle, but in the next 10, 20 years will be 90% of electric vehicle. And robot today, you don't have any robot, but in 20 years time, everybody has your own robot. Must be just like your phone. Your phone, how you can see 20 years ago, everybody had at least one phone. I have 3 phones. I have 3 iPhones. I mean, that's what we're going to happen. So I mean, in 20 years time, everyone should have at least one robot, maybe more than one. So that means the robot, how much power distribution you need, how do you charge the robot? You need a lot of the charge everywhere. You don't expect a robot to charge it within every half an hour to charge it. You have robot sufficient energy to charge maybe like a phone every 2 days to charge it. So you have good power support, good power distribution, good charger for mobile and also for your EV. And also for data center, for all the AI, we need to use data center. Now we're building so many power sources for data center. Every time when you ask a question, they consume 1 watt power. But how many questions you're asking? So how much power we need in the near future? So we need to build so large capacity of power source. So that means power distribution, power system is so important. Anyway, later on, if I have time, I give you some statistics. I show you what's happening in the statistic. But anyway, so this gives you the configuration for 3-phase, how the 3-phase look like. I think you've seen that. I mean, you can go home to use MATLAB or use whatever you like to do a simulation. You can see how they look like. And then for 9 voltage will be the phase angle will like that. The voltage will be 1.7 something amplitude as compared to phase voltage. So now then, when you come back here, let's look at the modeling. So next thing why we talk about 3-phase, because we need to model the induction motor. Most of induction motor, we tend to understand by the 3-phase system. So for instance, if we got the stator and rotor, or operate the stator, as I mentioned here, we connect the 3 winding either in star connection delta, depend on how you like to configure. Or maybe you like to have star connection or delta connection. And then for the rotor will be quite kind of the controversial. We all know that the rotor is not 3-phase, it's multiple phase. There's also short circuit, right? And then of course for pure mathematical analysis, everybody tend to make it look like a 3-phase and easier for us to analyze. Fair enough, because even though we configure them as 3-phase, we still using each of the phase produce their top and add together to become the output anyway. So that analysis has been well established, so we can still continue to use it. And so that means many of the modeling, they tend to use this configuration to say, you got 3-phase in the stator and 3-phase in the rotor. We try to analyze all the equivalent circuitry equation to work out the top and the. So that's how we try to do. So we now have some terminology here. The supply frequency, F1. Out in the rotor frequency, we have F2. So 1 being stator, 2 being rotor, similar to the primary circuitry and secondary circuitry, like in the transformer. We use similar terminology in the transformer. And then for 3-phase supply voltage, of course, we have 3-phase, phase A, B, and C, and the voltage we supply to them must be this kind of the format, will be different by 120 degrees. We see that because each of the winding, we try to see what kind of the current voltage and power for each of the winding and how the magnetic flux being generated for each of the winding. So we tend to analyze the motor by using the phase analysis, only analyze per phase. Referring this inductor or this winding. We don't analyze them between the line. We don't analyze them the line of the tube. Because you know inductor, they are also phase angle and really complex. We don't know that. We only analyze this one. So the analysis we do here, we call it per phase analysis. We work out each phase performance, and then for 3-phase, we set multiply by 3 or adding 3 phase together. This more commonly we tend to analyze a motor. So that is the circuitry. We can use it to represent induction motor. That's only for the stator first. For stator, if you look at per phase, each of the phase, you look like that. So firstly, the input side, you've got the resistance. R1, that will be the stator resistance, like the copper resistance. And then the winding will have magnetizing here, when you that have with some magnetizing, that will be magnetize the magnetic core, the lamination core. So that's how we come up with the magnetizing. So we call inductive. That if you measure inductance, we tend to measure this one. Just like we measure perform. However, there's some of the magnetic flux is not linking to the magnetic core. That's due to the leakage. For example, when we do the winding to any magnetic core, we presumably all the magnetic flux will circulate around the magnetic core for the stator, but some flux can go to outside the air, then we call it the leakage. So that amount of the inductance we call the leakage. So that means this one. So that's how we can see the inductance and resistance of the stator look like. So that means the stator current will called I1 will go into here, then pass through all the series components. The leakage more look like series component because it's not performing the magnetizing to the magnetic core. And then the magnetizing here will generate magnetic flux here, that will create us with the air gap flux to pass through the air gap to the rotor. And the voltage we induced in here called the E1. So this E1 voltage are mainly come from the magnetizing inductor. The input voltage come from our per phase voltage. Like the phase voltage, it will be appearing here. And then the current, we try to generate magnetization here because IM is the current, the equivalent current, how much current can go to the magnetizing. There's another term called IC. So as I mentioned, similar to a transformer, this current is not really measurable with just a model. What happened here will be, you can imagine the copper here resistance. You got leakage not linking, that's also important, not linking the main core. You got main core linking here, but we don't have that resistance in the induction motor or maybe in the transformer. It's only a part of the representation. Say this look like the core losses. Whenever we got the magnetic core, then there will be core losses that will due to the eddy current losses in the magnetic core, and maybe so-called due to the some hysteresis losses. So this core losses will be something the dissipation in the magnetic core. So this is in terms of the willpower dissipation. And then we lump them into a term we call the RC. And then we try to always put them across the magnetizing here. So this term is only measured. It cannot be measured. We just lump all the losses into a component called RC. So that's how we represent them. So that's all the major component or parameter we can see in the stator. And the E1 is the voltage we try to connect it to the rotor. So that's how we see the stator look like. And then for the rotor circuitry, then we have the E2, which we induced from E1 voltage for magnetizing across the air gap to the rotor circuitry, E2. So we have E2 voltage going to appear into rotor circuit. And then we also see that last time we also mentioned that we got S ratio. The S are mainly due to the induction. The air gap flux will go to the rotor is rotating, air gap flux is also rotating. The difference between these two is the induction. So amount of induction appear in the rotor side, we have S ratio here. So total voltage will appear in the rotor side, we have the E2 voltage due to the turn ratio transformer, plus the S here due to induction of the between the stator and rotor. So that mainly due to induction, but we see that there's a turns ratio due to the turns. So total voltage you can appear there will be SE2. We also show you one tutorial we did in last chapter, right? So that's the voltage. So that means this voltage, this current will therefore equal to ES2 and divided by this, all this component. So firstly, we need to examine why that component come from. So R2 is just purely the resistance in the rotor, just assuming the resistor, the rotor resistance, the rotor winding with a resistance there, then we call it the R2. And then the rotor, we also have the rotor winding. This rotor winding, we call the X2. But we found that the X2 here, we got a parameter, S here. S is the slip, the slip frequency is the difference between the rotating flux and the rotor rotating speed. So that is how much voltage being induced in the rotor. So that is also the frequency appeared in the rotor. So that's why the S here represents the frequency in this circuitry. You see all the inductance, their reactance are proportional to the frequency. So that's why I got S here to represent how much frequency appear in here. So you can see that S usually will be small, like normal operation motor, the S equal to say 2%, 3%, 5%. So that's how we can see the inductive reaction look like. So that means you can see that when it's in the standstill, when the rotor is not rotating at all, that reaction will be just like a transformer. So that means we got full voltage from the stator go to the rotor. And then when the rotor is rotating, when the rotor pick up the speed, just lagging the rotating flux by a few hertz, that means the slip will be only a few percent. Then that is the frequency of the rotor. So I think you know that the frequency in the rotor will be equal to the difference between the two frequencies. So we did a tutorial like that. So that's why this inductance, we got the X ratio here to represent the frequency. Because the frequency is not 60 hertz. It now dropped to a few hertz. You got S ratio here. So that represents because all the inductive components are proportional frequency. So now then we got this formulation. And then the real power is I squared R2. And then the S now in here, I can convert the equation by divide both numerator and denominator by S. So that means the S now appear in here, right? So that's the formula. So if doing that, then this, we can rewrite the circuitry into this new format. So now input voltage become E2, and then we got the X2 in here, and then also R2O for S. So now then we can circuit will be represented by this method. So that's the rotor equivalent circuitry. So you can see that the resistance here is R2 over S. So you see S is really small in normal operation. S is really small. So that means here you can see the R2 over S can be really large, especially when the motor rotates to near the zero crossing. Near the zero crossing point, like in here, you can see, imagine, you do have a curve, yeah. In here, S is equal to 0, or maybe close to this point, maybe S equal to 0.001, then nearly, so by that point, we have no induction, no power output, just look like open circuit in the one side, right? Why at that zero crossing point, when S equal is really small. So that can highly related to what we observe in here. So when S equal to close to 0 or 0.0001, close to the zero crossing, no induction appear. So that more look like an open circuit. That means the rotor at that point more look like open circuitry because no power goes to the rotor. That agree with our thinking in the torque and speed characteristic. You get that? Any question up to this point? Okay, good. So now then, you can see that our number of case study. So in the standstill, when S equal to 1, then when the motor just trying to start, the motor will be stationary equal to 0, then S equal to 1, then you can see that the total losses will be just equal to the rotor resistance. So the current becomes the rotor resistance. So that means the the relative speed will be between the rotating thrust and the rotor will become the synchronous speed. So that means we have the total 60 hertz. We're going to cutting our rotor. And then the induced EMF will be the maximum, because in this case, the rotor and the stator just look like a transformer. All the voltage induced from the stator will transform into the rotor. So that's why the E2 voltage will become maximum, because S now equal to 1. So that's similar to what we're thinking. When a rotor is not rotating, it's just like a stationary transformer. The voltage from the stator will transform all into the rotor. And then right at the synchronous, then that means the rotating thrust and the rotor are together at the same speed. So they are synchronized together. So all the rotating thrust is not cutting any rotor, no magnetic induction in the rotor. So no power being transferred to the rotor. So that means the resulting EMF will equal to 0. The voltage equal, you can from the formulation, you got S E2, S now equal to 0, no voltage induction, no voltage appear in the rotor. That means the current equal to 0, no cutting. So that means induction become negligible in here. So then between these two is the normal operation for the rotor. Then you can see that the voltage now equal to SE, E2, we got certain voltage. S is between 0 to 1. So the voltage will be have this kind of range. We can do see the voltage appear in the rotor circuitry, and then the rotor must be spinning slightly less than the synchronous speed. And the relative speed is the synchronous speed minus the rotor speed. And then we also call them the slip, right? So that's the 3 stage we can see in the rotor. So you can see that they all agree to our equivalent circuitry. So our equivalent circuitry for the rotor appear as this. So R2 over S agree with what we can observe in the rotor circuitry during the standstill or normal operation, or when they are synchronized to each other. So again, we need to look into the frequency, the rotor frequency and the induced EMF. So a few equations we try to remind you all. So the voltage induced in the rotor depends on the relative speed between rotor and the rotating thrust. That's what we have been talking about for quite some time. So at standstill, S equal to 1. That means when the motor just starting, the rotor is not rotating. The rotor frequency, just like a transformer, or the F1 frequency in the stator will convert or transmit to the rotor. So rotor frequency at that time equal to F1 frequency, the input stator frequency. So that's reasonable, like a transformer. So this like a transformer. So in normal operation, then the rotor frequency need to be multiplied by S. So S is the ratio between 0 to 1. So whenever we have normal operation, S will vary between 0 to 1. So the frequency in the rotor will also change in such a way. So I think we do have a table to show you the calculation some time ago, right? Yeah, like this table. So I think we did that. We confirm all this formula and all this correlation. I just repeat it again, make sure you can remember that. So again, I will remind you again, the voltage induced in the rotor have a 2 correlation. So we have a E2 is the transformed voltage due to the turn ratio plus a slip correlation in here. The slip will further reduce the voltage by the slip ratio. So the rotor impedance is something we also need to look into. Yeah, the R2, the resistance, cannot be changed by the frequency anyway, because that's a purely resistive. But for all the inductive component, like the lead gauge, then we need to look into the frequency. The frequency in the rotor circuitry are mainly controlled by the slip. So that's why you can see that. So H2, the lead gauge inductance in the rotor side at standstill, of course, equal to 2 pi F1 L2, right? But now then, when the motor start to rotate, the frequency for the rotor start to decrease, right? Decrease down to 0 with a S ratio in here. So that's why you can see that in the operation, the impedance will therefore has a S in here. So more look like the reactant will become SX2. Just like originally, X2 is the reactant in the standstill frequency. But now then once the rotor start to rotate, its frequency will become lower. So we got S ratio there. So the total impedance we can have, therefore, with now can provide by this equation. R2 is the real term, is not change with the frequency, and the X is the reactant term that will be vary with the frequencies. So now then the power equation also quite special. So of course you can see that the resistive term will be this one. This 2 is the resistive term, so R2 over S. The total resistance, the total power associated with E2 circuitry will be equal to R2 over S. You do remember that? That's how we get that, yeah? We can that. So this is the losses. So the power will appear in this loss, R2 over S. We divide it by S by using the equivalent circuitry. So that's why in here, we have R2 over S, which are our losses. Then you can see that this term is the copper losses. P2 is the copper losses, right? So that means it becomes P2 over S. So now then we're doing something special. We try to divide this equation 9 on 3 into 2 items. So you can see that these two add together still equal to that one because we minus here, negative, and then we are positive here. So we deliberately divide them into 2 components. There's some special meaning in that. Once divide them into 2 components, we can see that which is these 2 components. This will be fixed that relate to the copper losses in the rotor winding. And the other one will be related to the speed of rotation. So that means that will relate to the rotating power. Later on we can confirm that. So that means the power we transfer through the air gap to the rotor circuitry usually must have 2 portions. One must be the resistive power loss due to the copper. Another one is mechanical output. So we can, once we divide them into 2 portions, this is related to copper loss must be. The rest of them must be mechanical output. So that's why deliberately we divide them into these 2. So this is the ratio in here. You can see 1 minus S ratio. And I think in the table we list in the first beginning, we also show you about correlation between the 2. When we have first table to show you this, right? I think you do remember that we have copper loss and also mechanical power. These 2 ratio, one will be S, and another one will be 1 minus S. We did mention that. And then now then in our new equivalent circuitry, we try to demonstrate the correlation between S and 1 minus S. One will be mechanical power, and another one will be the copper losses due to the resistance. So then we try to divide them into 2. So that means this term is the speed dependent because related to S. That must be the mechanical power. This without any S term is I square R must be the resistive power loss due to the copper. So now then we look at that. In this equation, so this term 1 minus S, so this is our so-called air gap power. So the air gap power, when you transmit across the air gap, we have that will be our mechanical power. And the air gap actually equal to P2 over S, right? So that will say our rotor copper loss now is I square R2 is equal to S portion of the air gap power. So now then we now establish a correlation between the air gap power, the power passed through the air gap, and P2 is the copper losses, and mechanical power is, so the ratio become 1S and 1 minus S. So that's how we come up with the final conclusion, how we can see the air gap power relate to the mechanical power and also copper losses. So we are using this equivalent circuitry. We're able to now begin, in the beginning, we have this ratio. So now then we can see that 1 minus S in here, S in here. That's how we get the air gap power. So that's quite interesting. It seems everything are correlated to each other really well. By using a simple equivalent circuitry, by using the change the frequency domain into S domain, you're able to differentiate one will be copper loss, one mechanical losses, how they relate to the air gap power. Air gap power, the power transfer through the air gap from the stator to rotor. So that's why this kind of mathematics is simple mathematics, really simple modeling. We're using a simple modeling, we're able to develop a quite important concept, how to relate all the power together with a simple correlation. So that means the final discovery, major conclusion will be just like 1S and 1 minus S. So that means the mechanical power is only a portion 1 minus S ratio for the air gap power. Okay. Any question? You may need a bit of time to look into the math, but the key conclusion is really interesting. So we have very simple and beautiful formulation, how to relate each of components. In the rotor, we only have a few components. Copper losses in the copper winding and copper bar, right? We also have out power mechanical in the shaft, and also power goes through the air gap from the stator to rotor. And then they have a really beautiful correlation is such related to S. That's why for all our analysis, we tend to use the S to relate to everything. We don't use the speed. The speed is more true, it's not inconvenient quantity. Once we convert S, which is in the normal line format, normalize everything into S, then we're able to obtain a really beautiful relationship of all the power. So this work has been done by last 100 years. So really interesting, but we still continue to use it. And it's also really not interesting. Let's see, we only have a few minutes left. So now then the total equivalent circuitry, we can put these two together. So you can see that just now we have this circuitry for the rotor, we have this circuitry for the stator, and then they have an E1 in here. So this E1 to this E2, we have a ratio. What are ratio between them? If you want to put the stator circuit and motor circuit together, become a complete circuitry, then we need to deal with how to connect E1 on the stator and E2 in here. And E1 and E2, I've mentioned that it's just not like that. I think you know the answer.
Can you repeat the question? Sorry.
The E1 and E2 voltage. What I'm trying to do will be, this is a rotor circuitry. And this is a stator circuitry. I want to put two circuitry together into single drawing. But one is using E1 in the output. And this rotor circuitry, we're using E2 in the input. If I want to put them together, I need to equate E1 and E2, right? E1 and E2 are related to one simple ratio.
No.
Not. It's really a lot of memory because we go through so many equations, so confused. It's the transformer turns ratio. Yeah, transformer turns ratio for between the rotor N1 and N2. So now we connect together. A is just the turn ratio. Yeah, because when stationary, they just become a transformer turn ratio. Now then we connect them up here, but the A here. Once you put the A, then we put the A square in here in appropriate term to put them all together. Once we do that, because the current have the also like transformer has an A ratio here. So now then that's a final circuitry. We are putting the everything together become total inductor equivalent circuitry. So this equivalent circuitry you can see in any textbook, any internet, all the internet, when you search up equivalent circuitry, they also show you this diagram. It's very common, well-known, well-accepted equivalent circuitry. So you can see that input voltage V1, when you pass through the circuitry, then we convert that into A ratio, which turns ratio between the stator and rotor, then all the ratio S, which is the frequency dependent. That's a copper losses. And this is a lead gauge and lead gauge, and we also have copper resistance here, copper resistance here. So that complete the whole model. So that is a really important concept. Why we need to use the equivalent circuitry? You are able to use that equivalent circuitry, understand to relate all the power, frequency, and also write down a really simple formula to understand. You see, induction motor is so complicated. We can now using a simple circuitry to represent it. And even though all the power, air gap power, mechanical power, copper losses, they're all so simple now. So that's how we're going to do that. So in the exam, you don't need to divide formula. You only need to know the result. That will be good enough. You only need to know how to do calculation. When I was student 40 years ago, I don't quite remember the equation. The equation is so many, probably quite complicated to do that, but you can able to make use of result that will good engineer how to design the induction motor. Yes?
So just to make sure, is this the equivalent circuit of all three phases or for just one phase?
Per phase. This is per phase. U1 is a per phase voltage. Three phase we have three of that. This one only for one phase. It's the total power multiplied by 3. That is not line voltage. That's a phase voltage. So multiplied by 3. So that's all. I will see you again next week. Thank you.